It's really fun to be here, especially after Danielle showed us how wrong all predictions about the future are. And now I'm supposed to show you what I think buildings of the future might be. But what I decided to do today is to tell you basically what we see in our practice and what I take away when I step back. And this idea of low tech versus high tech, really something that I see emerging in our work relative to climate responsive buildings. So first, just the quick introduction to Transsolar. If you don't know us, this is actually my 10th year now with Transsolar, 10 years since I left Chicago. I'm leading the office in New York, but we've been around for actually more than 25 years now. Very small, but international firm based in Stuttgart. We also have offices in Munich and Paris. Doing this idea of climate responsive design, really a very tightly knit group of 50 engineers from around the world doing work all around the world. And we focus on this idea of climate responsive design, working very closely with architects and the entire design team. And the one very simple way we love of describing what we mean by climate responsive design is that rather than taking something that is inherently not efficient, not such a great environmentally responsible design like a Hummer, and then strapping a bunch of gadgets onto it, so you got your biomass wood generation and some gray water recycling, a wind turbine, and put it at transit-oriented bus stops. And now claiming that it's green, we say no, that's really not the way we should be doing things. We're really interested in climate responsive design from the ground up, where the entire decision-making process for that object you're creating, for us usually buildings, but it could be anything, in this case racing boats, is around the performance of that object, but that also informs the design with a capital D, black shirt design, whatever you want to call it, so it is also a beautiful object and useful to use in it, to enjoy in its own right. And how do you accomplish all of those? That's the kind of idea of climate responsive design, is really that design from the ground up, working with the climate. And today I want to share with you what I thought about the future of our own work, this really interesting divergence, or convergence, I guess, but what has been a divergence, even if we just focus in the last 10 years, of a set of very low-tech projects, extremely low-tech, that we've been really lucky to be involved with, together with a set of what I would say, especially in the US, we're much more well-known for super high-tech projects, and climate responsive design means you do double facades and super high-tech and so on. And only in the last 3 years do I suddenly begin to see some kind of convergence of those two, which I think is really interesting, and what does that mean for all of us? So starting with the low-tech projects, what do we really mean by that? And more than anything, when I say low-tech in the context of climate-responsive buildings, to me that means no systems at all. Buildings that just use the fabric of the architecture, the way the building works, with no heating, no cooling, no mechanical ventilation, sometimes even no lighting, in order to make the space occupiable. That's how we originally built buildings until about, I didn't think this out, I just think of this just now, like what, 200, 300 years ago that we started putting this stuff in buildings in order to make them more comfortable. And how do we make them comfortable without relying on that stuff? So the first example is one of the very first projects, which I think is over 10 years old now, that we were involved with in Damascus. Actually, unfortunately, it's been damaged from the war there since all these photos were taken. But it was a school, a French school, and the parents for the school really needed something very simple. They didn't have a lot of money. They wanted something to be very easy for them to maintain, but they wanted to be comfortable. So the mandate, it's very, very helpful when this is the mandate, you don't have to argue about it, was no air conditioning, like that, because they don't want to forward or maintain air conditioning systems. And in Damascus, they have this kind of climate engineer's dream of a classic high diurnal swing climate, meaning it gets really hot during the day, but it gets very cool, well below 70 Fahrenheit every day at night, meaning you can take advantage of that using thermal mass, so that during the day the windows are actually closed and all the ventilation air, you got a lot of kids packed in there, so you need ventilation so it doesn't get stuffy, enters through the tubes that you see underneath there, which are cool, and that cools down the hot air that you have coming in for ventilation. All of the mass, the concrete and so, gradually heats up over the course of the day. By the end of the day, it's just a little bit warmer. You need to cool it back down for the following day, so the teachers and students, before they leave, they actually have to open the windows, and then you have this chimney that stays warm through as the sun sets because it's facing west. and that really continues to draw the cool night air in through there and cools it down. And so this building has, it does have some ceiling fans, it does have some lighting, but there's no mechanical ventilation, there's no cooling. It's a very, very, very basic heating system that they barely need to use, and really had a fair amount of success. And I love starting with this project because the diagram of how it works as a building translates very, very literally into what you see here in the built product. With this section, you can see the chimney sticking up, you can see the stack that just has 2 classrooms. There's actually these courtyards outside as well. And so this is what we mean by extreme low tech. That's not even glass on the solar chimney, it's actually just polycarbonate, because cheaper, simpler, easier to maintain. Inside of these courtyards, it's really very nice space, and you can just barely see, for those in the center here, along here is where that air gets drawn into the tubes underneath, and there's a little bit of temperature reduction just from the vegetation and shading and so on that you have in the courtyard. So that kind of strategy we have found then successful in a variety of these, what we use the term majority world locations, which is where we call it majority world because it's where most of the population of the world lives. It's not in Western world where we can afford all these fancy and complex systems. So this is a project just outside of Pune in India. You also notice I'm not going to have time to acknowledge them all, but we'll always list the architect because the integration is so close with the architecture on these type of projects. So this is using the same strategy, bring air in, especially for the classrooms that are the lower 2 floors, and then there's dormitories because it's a residential school for girls, with the girls living above and exhausting air out of the top. And this was completed just more recently, about 2 years ago. And so very, very simple with the dorm, which just draws air directly from outside because it's less densely occupied than a classroom. A classroom is much more densely occupied and therefore needs a little bit more cooling, and therefore the space underneath the building again is used to pre-cool the air before it goes into the classrooms. The classrooms also need to be able to close their windows more because it faces onto a busy courtyard and they need it to be quiet. So rather than pulling the air directly through the windows, it comes in from underneath as well. And here again you can see this, where the air goes into this cavity, which is just between where the spaces back up to each other. So these are the kinds of things I mean when I talk about low tech, and I show these 2 majority world projects, but a Western project as well. One that we Transsolar had nothing to do with. I don't know that much about this project, so please don't ask me questions about it afterwards. It's called House 2226. That's 22 degrees Celsius and 26 degrees Celsius, which is the temperature range that it was designed for. And this is actually an architect in Austria, their own office, and this has absolutely no systems, and gotten a lot of press for that. They've challenged themselves to design an architectural office that has very thick thermally massive walls, is very well insulated, has no mechanical ventilation, there's no heating system, there's no cooling system, no nothing. It's just kind of amazing that they're more or less making it work. One reason is that how do they heat it? They have a lot of people, they have computers in there, they even have lights, and maybe when it gets really cold on, they have to leave the lights on overnight. So there's the very old, even Chicago idea of heat by light, if anyone knows that, from the 50s or 60s. So the old idea is made new, but at very, very low power. So kind of picture the interior. It can may have different feelings about that. It's super stark there, and you see there's no lighting installed in the building at all. If they have some lighting, they have to bring it in, and the panels on the side for next to the window for ventilation. So I'm going to contrast that with high-tech projects, which will tend to be the more kind of Western type projects. And the first is Manitoba Hydro Place in Winnipeg. It's really sort of a flagship for us as a high-rise project that is based on a whole series of zones that are connected with this south and north-facing atrium and double facade. I'm not going to try to explain how all these pieces and parts work together because I just don't have time to get into that right now, but there's a winter mode where these atriums are interconnected and the double facade is closed and sealed, so it's super insulated. There's a natural ventilation mode where the facade opens up. The entire exterior facade is what you see in my high-tech image here, where the entire facade is automated. There's an actuator on all those windows. It all opens up. And that draws air up out of still actually a solar chimney, what we saw in the low-tech projects. And some idea of what it looks like. There's pairs of mechanical ventilation units that are concealed in these benches here and there. And the chimney that drives the ventilation for that kind of creates an icon. We have some of these kind of high-tech projects here in Chicago as well. How many people know this project or have been there? Info comments at Loyola. So I don't want to spend a lot of time on that, but that uses a lot of the same ideas, and I think, again, is a great example of the very climate responsive, but super high-tech version of the climate responsive design. Based on, again, always thinking very carefully about different modes, and it's not just heating and cooling, that you have a natural mode where you open up to outside, but there's a lot of glass, so again, there's a double facade in order to respond to that, and you have to have all of the controls working in the bits and pieces, coordinate and understand the idea of how both the architecture and the mechanical systems fit together as one integrated system working together. And this project goes another step as the first time that as another high-tech version of something that's relatively low-tech of radiant that's embedded in concrete, which is very common, but doing it in precast, which we've done several times since then. But this project was actually the first project in North America I know of where they embedded radiant tubing in precast concrete. And here's the look inside the double facade of that for those of you that haven't been there. And kind of, again, very high-tech when you go complete transparency with the cable net wall that they have there, and you can close it with the blinds and so on. So. And just another example of that, Loyola has been really lucky of continuing with this series of these kind of high-tech projects. And again, the double facade on the big south-facing atrium of the business school that just opened last fall, I guess, something like that, downtown. It's at State and Pearson. And the diagram from SCB showing sort of the same concept there. And this is also using a lot of the same concepts. Just to make it clear that it's not just low-tech projects in majority world and crazy Austrian architects, and that we're doing these high-tech projects in North America. I think a lot of people know it's probably not the case, and they're used to seeing these kind of projects come from Germany. And of course, yes, there are a lot of these in Germany as well. So this is one of ours, is the KfW Westerarkade. And this project is so high-tech that it has this pressure ring controlled double facade with the idea that the wind is flowing around the building. Air will not want to go into every window because some of them are the leeward side of the building. You have negative pressure on the leeward side of the building. So how do you force it to be positive pressure on the entire side of the building? You make it like a facade that's like a tire wrapped around the whole building, so the whole thing is pressurized by the wind. And that's why all these colored flaps that you see that are open and closed in order to open more on the windward side and induce pressure, have this positive pressure of ring all around the building. Boy, that sounds really cool and exciting, but it's really high tech. And the controls, the theme of the day here might be controls, really have to work right for that sort of thing to work. That was all kind of a unitized facade system. You see the typical module with it going in and the kind of the result. And then just to end on the high tech versus low tech bit here with another project that, again, actually we weren't involved in at all. I know very little about this project, so please don't ask me questions about it afterwards, but how many people have heard of this project? Only one. I'm really surprised, honestly, because this project has gotten an enormous amount of press called the Edge in Amsterdam. And this has especially gotten press for the use of technology more in the way that Danielle mentioned on with the robots, that they have the app for finding the room and all the wayfinding in the building. They have the robots that go around and do the cleaning, all of the conference room scheduling and so on. It also has some climate responsive aspects, although I don't know that much about them because you can't find them in the press because they don't seem as excited talking about that, but it's still the idea of the use of technology in the building. This is one of the reasons it's so well known. I mean, there's this tremendous, glowing, huge feature article in Bloomberg Business Week on it, called it the smartest building in the world. I think that's a really strong statement to make about any single building. They're really, really hyped up about it. So kind of another example of the really, really high-tech approach. So when I look at these, and I thought a little bit this week about, when I look at our work today, I'm going to show you some examples in just a minute of how these two things I actually discovered are a little bit coming together, which I find very exciting, this idea of let's use technology in the way that's appropriate, in the place where it really is most effective. And actually, I think it comes back a lot to this use of technology with a capital T, the way we usually use it in US corporation world, where we talk about tech means the tech industry. And the use of technology in buildings with a lowercase t, systems and so on. Let's keep those as simple as possible, and the use of tech with a capital T enables us to start making simpler and fewer systems than we used to have in buildings, together with the way we do it in architecture. But why do we do that? As I was kind of developing my new thesis for you here today, we sat down and discussing with one of my colleagues, well, why is that? Why, whether it's low tech or high tech, why do people want to have this kind of climate responsive design? And why do we find them using either of these responses in order to do it? And I came up with kind of 4 big reasons. One is this idea that it's not just about energy efficiency is sort of the takeaway here. Of course, all of those things result in energy efficiency, but the real driving factors are this idea of delight, of being excited about the space you're going to live and work with every day and the way you interact with it. That results partially from variety in time and space, and that actually, there's this great podcast I can give you the address for later that talks all about the idea of thermal delight, if anyone knows that classic book on thermal delight, and that thermal monotony, the temperature being the same all the time, the light being the same all the time, is really boring and not healthy, and people really prefer to be spaces that have some amount of variation. They also want it to be intuitive and participatory so that it's not a hidden thermostat and secret systems that are doing things. You have no idea how the hell the space you're in working, but it's very obvious. I want fresh air. Here's a big handle. I go up and open this window, and now I got air. It's so simple. And then as a result of doing those things, of course, you also get some resource efficiency. So the reason I ended up with this kind of idea of contrasting high tech and low tech is looking really just in the last 3 years, I see a lot more of our work beginning to bring that together. So the first project is the School of Business Administration at Portland State. It's together with Banish, who we do a lot of work with. And this, as far as we know, this was a renovation actually. This kind of silver part in the background is a renovation, and my focus is on this new construction portion, which climate engineers' dream is like the Pacific Northwest climate, super mild. You think, oh my God, this is the place in the US where we can finally avoid air conditioning. But this is the first modern commercial building in downtown Portland, Oregon, built without cooling that we know of. And it didn't happen easily. It was a result of a lot of discussion. If anyone actually read my, or I had an abstract, but I was going to say about what it really takes to make this happen is thinking about the expectations of occupants, expectations of owners, how facility staff will interact with and maintain a building that's thought about totally differently, and what the systems are. And so in this case, agreeing on the metric and how we measure what is acceptable for a building without cooling, and overheating hours in this case, and then looking at how the impact of different measures, adding the ceiling fans, having correct orientation, the night cooling, and so on, all sum up to get you below the metric that you need. So now the building is open, and the other part of my message with this building is we're going through our first summer. I was a little bit scared about the first summer, and you might guess, like, not everything is working perfect. Surprise, like that's what happens with almost every building, but the secret is that it's not about complicated systems, it's about controls. Guess what? The controls aren't working properly. I'm sure every commissioning agent in the room, which I think we have a lot, is not surprised to hear that. But even though we thought it was all very clear what the controls are supposed to do on something that doesn't have a lot of systems, the building that's supposed to work with night cooling, the windows aren't opening at night. Like, come on, guys, let's fix this. So as you go to simpler systems, the role of controls in the remaining systems that you have becomes even more important. It doesn't mean that you're eliminating all complexity. You're just applying complexity in the right places. The next project I want to show is the TRCA, Toronto and Region Conservation Authority headquarters. This is with an Irish architect. They're the one that did the project with that window that I just showed with the guy opening the thing. And if anyone believes in eliminating systems more than us, it's these guys. So trying to figure out what do we do when we bring them from Dublin, where you can really get away with no systems, to Toronto, where you can't really do that, has been really fun. And this is the kind of most basic diagram that the project ended up with. And what I'm excited about when I say low tech on this project, because there's really no ductwork at all. It has these 2 atriums, and the idea is that even if you're in a mechanical ventilation mode, you have this visible shaft that's very large, and the air is drawn in down through this shaft. It's almost like a glass duct or something within the atrium, and that connects to decentralized, very small units. There's no big fan rooms, big mechanical units, just small decentralized units that do the heating and cooling of the air and deliver it straight out into a raised floor. So there is still some of the technology that you see in a building, but it's trying to decentralize it, make it a little bit simpler, more robust. If one of those fails, the rest of the building is still working fine. And then the south facade is taking advantage of all the huge amount of solar gain they get on the south so they can still open the windows on the southern half of the building even when the northern half of the building has to go into mechanical ventilation mode. This kind of diagram is showing kind of the same things. So you have these units that pull air off of the things pulling in. And again, the discussion in order to make this work and with some different modes, here we have this idea of this natural ventilation preheat. That's what I'm saying when it's, you've got the solar gain on the south and you open windows on the south even though you don't have windows open on the north. And we find no one is used to thinking about this idea of different modes and that the building changes modes. It's a dynamic, even though the architecture is static, the behavior of the building is dynamic and the temperatures are fluctuating, and that's an okay and good thing. Or you also end up with the perception that's happening all the time. So this was evaluating over the course of the year. These charts show an entire year from January to December and the hours of the day. What times of day on each day of the year for a typical year is operating in those different modes, so they can really have an understanding of what are they getting when you talk about, like, okay, is it kind of low tech, is it high tech, how does it work, what is it really going to be doing, putting in a picture like this is how it switches between different modes and so on, and then what are the temperatures as well. So how, if it's going to get a little bit warmer, how much longer will it get a little bit warmer, and when does that happen, what will people be wearing there then, and so on. I have two more examples to show you. The next one is the School of Design. This is under construction now for the National University of Singapore. Project, again, with super high ambitions, aiming to be net zero energy in a really warm and humid climate. And the response here, I would say, is twofold when we talk about this, keeping things a little bit simple. Is all of the circulation spaces are just completely open in these kind of tropical climates. It's something that you see often in kind of resorts and so on. When you go to tropical climate, all the circulation is totally open. You have smaller cellular spaces that are more conditioned, but you don't typically see it in commercial buildings. So it's a commercial building that takes that same approach. But then all of the, except for a handful of computer labs and so on that have, quote, full air conditioning, the remaining spaces, especially the studio spaces, it's an architecture school, and so all the studio spaces are sort of a real highlight space in the building, I would say. I have what's labeled here as hybrid. This is green. We have started calling it soft cooling, which is really challenging comfort expectations, and is even harder, I know, in North America to get people thinking about. But the idea is that rather than fully dehumidifying the kind of humidities that people are used to designing mechanical systems for, designing for really low temperature set points of even 75 or 76 Fahrenheit, of dehumidifying much less, just cooling air down to 68 degrees, so it's just a little bit cooler than room temperature. That results in much lower humidities than outside, but much higher humidities than we have in this room right here, but also results in a lot less infrastructure. So this is comparing if you had whatever, a traditional full VAV system with ducted return and all these things, and then just a little bit of out air. It's just minimum fresh air that's cooled this amount, maybe a little bit more fresh air than you would usually use to give you better air quality. No return ductwork, not even trying to do energy recovery because it doesn't make such a big difference on hot and humid climates, combined with ceiling fans so that they will be comfortable at those warmer temperatures, and really challenging the idea of what expectations are in a hot and humid climate. And consistently we find that in order to apply that sort of simplified approach or rethinking what your expectations are for the space, you have to experience it. You have to go and experience another space that's been designed that way, or mock up or test it in some way. And so this was in Singapore, going to another school and operating it to be in the kind of temperature and humidity ranges that are expected for the architecture school. And after they did that, there was really a lot of consensus from the faculty, from the dean, and so on. They're like, you know, oh my God, I don't know, is this going to be comfortable or not? And you come into space, and it's like, wow, it's so comfortable in here. This is like so much better, and it makes the decision-making process so much easier. And so that's the idea of what this will look like as it gets built. I think it should be finished something like next year. We're always really happy when we see the ceiling fans included in the renderings. The last one I want to talk about is All Natura. This is a kind of like the Whole Foods of Germany. So it's a German organic grocery store. So of course, you can imagine what an American organic grocery store, if anyone knows how much Germans are into the organic stuff and so on, it's going to be even more over the top than a German one. And so this is using a lot of the same ideas that we see in the other projects so far. Again, I'm not going to try to explain the whole diagram. For those that are up front can see it. I'm sorry that it's in German, but what I really want to focus on is just the wall heating and the wall construction, because it doesn't really have any kind of central air handling system, just these earth ducts and so on. But it also ends up being one of the largest scale projects we've been involved in. That's also beyond rethinking the systems, thinking about the materials. As we reduce the energy use, we all know that the embodied energy materials become so important. And so whole building is basically built out of rammed earth. And there was really a goal to eliminate systems. Initially, the goal was to not have any heating or cooling, but the conclusion is they needed just a little bit. But it's so small, the amount of heating, that could get away with just having radiant tubing actually integrated in the very inner skin of that exterior wall itself. So it's really kind of minimizing the surface area that's needing it. And I just got these construction photos from one of my partners, and he was very good in his selection of pictures, recognizing that this looks a little bit rough. Maybe no one's so excited about a building that looks like it might not be so beautiful in the end. So some shots of the interior of the atrium is coming together, the kind of usual strategy with exhausting all air passing through the atrium, but then this spot where they actually have the facade finished. And looks like it's going to be really, really nice in the end, the kind of combination in this case of low-tech and high-tech facade materials. Very, very simple and basic rammed earth with the kind of storefront wall system that we see next to it. So I guess what I wanted to end with is I like to use this provocative statement that buildings are not spaceships. And when we talk about climate responsive design, that the Earth already provides us with this amazing environment that supports everything we need. We don't need to be buildings that seal us off from that in order to protect ourselves from that. The purpose of the buildings is just to provide shelter. And in this context, I thought it's interesting thinking about the future. People have been imagining that the future buildings would at least look like spaceships, if not operate like spaceships, for a long time. And I think that's definitely not the case, but there is something to be, that's not to say that there's no place for technology, that there's a lot of ways we can use technology. And I'm really excited about how the use of technology can allow us to simplify other aspects in buildings as well, but would also remind that the reasons that why we're doing that is the reasons that we're all in the industry of creating buildings in the first place. Is we want those buildings to provide delight. We want them to provide variety in time and space. We want to create buildings and systems that support those outcomes rather than just making them very static. We want it to be intuitive and participatory so that people are able to participate in their indoor environment. And an outcome of doing all those things is resource efficiency. Okay, I think I'm more or less on time, so we take a few questions now then. Yeah.
And if you could repeat the question.
Sure.
That'd be great.
Okay. John was first.
So how much do you think the previous experience of people in buildings has to do with the ability to work with the variation temperatures? Like, I'm guessing that here in the States we're used to having, we like to think that precise control is best. And we have the technology that controls all that, and so we expect a certain temperature all the time. Whereas in other parts of the world where maybe they're not used to having it in the
Right.
first place, they're okay with the water variation temperature. They're more tied into the outside environment. How do we move in that direction here?
It's difficult, I know, because I've encountered many that won't do it, that for facility managers, for example, to accept that that's something that they would try. But our experience is consistently, when you actually give a space like that to people, they like it. The Manitoba Hydro is the best example that it's active slab. There isn't a thermostat that people can adjust because the concrete slab is very slow responding temperature. They can open and close their windows. And when they moved into that building, their hot-cold calls for that building are half of what they have for any other existing building. And we're not always able to get data like that, but I'm a pretty sincere believer in trying, and that's one data point. We try to get some more that of course there'll always be somebody, we all know there's somebody won't be satisfied, but the vast majority actually like it that way. And you give other forms of control. Do you want the ceiling fan on or off? Do you want the window open or close? Oh, I forgot to repeat the question, I'm sorry. All right, but anyway.
Well, I'm going to piggyback onto that because what I was thinking of is your ranges are pretty wide, and in order to have that acceptable in an office, you're going to also have to address wardrobe and what people are allowed to wear. Do you see resistance? Some of these are big companies, and you can have one company has a policy, but if you're in a big office building that's going to have multiple tenants,
right,
they go in there and say, oh, we might have to change our corporate dress code. You might be in
right.
a t-shirt if it's 80 degrees inside the office space.
The question is about dress code, and that's a fair one. Like we just had a discussion in the office about business school, and a colleague was just there, and he was really happy because sometimes the report is that at business school, even all the students are wearing suit and tie because they feel like they have to because they're in business school, and that was not the case. But then we said, well, come on, it's Portland, Oregon. Like, nobody wears that in Portland, Oregon. But in general, we haven't had a lot of pushback on that, but it tends to be. Right now, I would say it's definitely easier with single occupant buildings who know their population and have control over it. I don't have examples to show you of kind of developer multi-tenant type buildings where you want to provide that flexibility. Or one option is that you have the capability to operate that, but if you want to operate it in a more super tight way, you can do that. The challenge is that then you have to install systems to support that, which you spend money on. Should we take time for one more question, or go on?
Yeah, are you going to be around?
I'll be here. Yeah.
Yeah. So
You might be getting.
The bar can ask one question.
Yeah.
Fascinating presentation. Thank you so much for giving this. My question is, all summer I've been hearing about how the Pacific Northwest and Europe and the UK are experiencing record heat. These places have somewhat climate responsive designs already, and now they're putting cooling shelters up and things to support that. How does climate adaptability play into this?
So the question was, how does climate adaptability impact this kind of approach or philosophy, which is a great question, and the answer depends completely on whether you're actually eliminating a system or not. I would say, especially on the cooling side, when we talk about climate change, that on many, especially North American climates, we're actually still not able to eliminate cooling. And once you keep some form of cooling system, what I find is that the climate change doesn't have that much impact because it's much more driven by solar load and things like that. And if the temperatures get a little bit warmer, it should have no problem. If you go the step of saying, like in Portland, we can get rid of it, then I don't think it happened on that project. But definitely in the future, that you have to use future forecast weather scenarios as well, and look at what would happen then. You have a discussion with the owner about, well, will this still be comfortable under this future scenario? Is it acceptable? Do we put in provisions so you could provide something in the future if it becomes necessary, but it's not necessary today? I think those are all discussions that any project going that direction has to have. Okay.